Hello everyone, welcome to Linear Model with me, Sarini Abdul. For this session, we will learn about external model validation. In the previous video, we already looked at the motivation of why do we need to do model validation. That is, usually we work on a sample to solve or to try to understand some problems, for example, and then from the data that we have in the sample, we do model fitting using the ordinary least square in this example. And after we get the model fitting, we do the testing of the goodness of fit of the model. If it is not good enough, we have to check our model and try to improve our model, whether the variables included in the model is strongly related with the response variable or not, or even if they are strongly related with the response variable, whether we are already putting in a correct functional form of the predictors or not in the model. So we need to do a refit our model. But if the model is good, then we check on the model's adequacy represented by, for example, like the coefficient of determination, adjusted R-squared, the mean squared error, and so on and so on. And again, if the model is not adequate, we have to recheck our model and try to refit the model. But if it is good, then we continue using the result for interpretation and use the model for prediction or even estimation. Up to this point, we are happy, but then we need also to consider whether the performance of the model is still good when it is applied to the new data, and that's why we do model validation. For this video, we will focus on the tools or the metrics of doing the model validation. The first one is that we can do evaluating the predicted values of the response variable or even the estimated values of the regression coefficient. And then we also can, collect new data. Or if we don't want to collect new data or we are not able to collect the new data, we can just do data splitting. Usually this is known as the cross validation. And we can also do jackknifing. What is it? We can see it later. Okay, so in evaluating the yi cap or the beta j cap, that because later on, that in the previous slide, we see that we take sample, let's say of size n, and here we get our line equation is that, for example, given by y equals beta naught cap plus beta 1 cap x1 plus blah, 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 plus beta p cap xp, for example, like that. And then to see whether this is good enough, we check whether, okay, are the expected, or are the predicted values of yi close enough with the actual values? If they are close enough, then that's good. But probably there are some points, some data points that far away from the predicted values. In that case, probably we need to again check whether we already have a really proper model or not that we fit into our data. We can also check on the estimated beta parameters. Let's say based on the context knowledge of the problems representing by the data, I expect that beta 1 should be positive. But then it turns out that the estimated value of beta 1 is negative. So seemingly like not as I expected. In that case, it's an indication that there is some problem with your model. So again, you have to check whether your model is already in its best form, or probably you really need to check your data, whether your data is already well prepared or already cleaned before you do the model fitting using the regression. Okay. Let's say we do this using our sample data, but then we want to do the external model validation, that is to assess the performance of our model when it is applied to the new data. So it's just reasonable that we need to collect new data And based on the new data, we calculate some metrics for the assessment. In this case, we calculate the coefficient of determination that represents the accuracy of our model when it is applied to new data. It is a new data because if you look at here, the observation from 1 to n is the one that we use to build the model, and here it is calculated for the new observation that is from n plus 1 to n plus m. So we collect m new data points. So our expectation is that this r squared for the new data should be as close as possible with the r squared that we have from the data that used to build the model. Probably most of the times r squared predicted will be less or smaller than this, but even so, we want the difference is not, I mean, there is no big drop of the value of r squared from the, from the data that we used to build the model and from the one that when we apply to the new data. Okay, so a good model, a robust model, will result in quite high r squared predicted and close enough to the one that we get from the previous process. The same idea is also with the mean squared. While for r squared we want it to be as big or as large as possible, we want the mean squared error here to be as small as possible. And in this case, we can most of the times that the mean squared error predicted will be larger compared to the mean squared error that we got from the n sample data in here. But we want it to be, even if it is larger, but the difference is not that much. In that case, we say that our model is good enough when it is applied to the new data. That's if we want to collect a new data, but sometimes we are not able to collect the new data because, you know, when we say about collecting new data, it's related to the, you know, resources. We need budgeting, we need human resources, we need to spend more time to do that. In the case that we cannot do that, okay, we just do kind of like data splitting. That is, okay, from the n sample in here that we have in here. So let's say we have that n sample, then we split it. So this is to do the modeling that we did before, then, and then a small portion of the data will be treated or will be considered as our new data, and then we can apply again the calculation that we have in before, like r squared and mean squared error. Okay, but then again, we can do splitting. Okay, we can do splitting if our data is big enough to do that. But sometimes even we don't really have enough data. Okay, so our data, when the sample size is kind of like small, relatively small, then even data splitting is not possible. But we still want to do model validation, then we can do the jackknife process. So jackknife process is kind of like data splitting, but instead of, for example, like in data splitting, usually we have the rule like 70-30 or like 80-20. It means that 70% of the data is used to build the model and 30% of the data is considered as the new data, or 80-20 in some other cases. In the case that we cannot do splitting like this, then we do jackknife. For the jackknife, this is also known as leave one out cross validation, which means that if we have n data points, 1, 2, 3, 4, blah, 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 up to n data point, then we leave out one data point each time we fit the model, and after the model is fitted, then we predict the data that was left out using the result of the fitted model. I mean that, for example, like this, for the first step, okay, using this n-1 data point, then we get that equation of the line, and then from this equation, then we can do prediction for the first observation that we left out when we built the model. So then we get that, okay, it should be like this. Okay, and then we compare our prediction here with the actual value of the first observation. And then we repeat that. Okay, next time, the second step, we leave out the second observation. We use observation 1, 3, and so on. And we get the equation for the regression line. And then, so we use this equation to predict the second data point, and then we compare it to its actual value. And keep going until the last step, that is, we leave out, for example, the nth data point, and then we just fit the model using the first n-1 data points, and then we get the regression line, and then we use this line to predict that data, the nth data point, and then we compare it with its actual value. And then according to this result, then we again can do calculation as in like the R-squared or the mean squared error, by considering that the one that's left out as the new data. So we can do this, and then again the rule is that if the R-squared is not, there is no sudden jump, I mean that no big drop of the value of R-squared, or the mean squared error is not too not very large compared to the one that we have from the our sample before, then there's a sign that our model is robust enough, and we are confident to apply it to the new data. So in conclusion, we can say that model validation is needed to ensure the consistency of the model's performance in new data.